Okay, so this is the SPCOM 2022 tutorial for generative models and role of deep neural networks. I gave these tutorials 2 days back, but then the organizers has requested me that I should give a recording to them. So this is the recording. Here I'll be much faster because I don't have any interactive discussion. So let us start. Here to show some examples of the generative models, just to give you some basic ideas and to attract the attention of the audience. I will talk about the generative adversarial network, it's called GAN, later, but here I'm showing you how it has improved over the time. So original GAN paper in 2014 was able to generate, this kind of facial images. Why facial images? Because every facial image is quite high dimensional. For example, let's say this is 100 cross 100 pixel dimensional image, then it is 10,000 dimensional image. So it is generating, such kind of images. And every face is different, actually, that human mind can understand that every face is different, and this is very difficult to order till the attributes, how the faces are very, each person is different. So here you can see that in 2014 the system, the GAN system, was able to generate these kind of samples, and these are the samples. You can think like that, the faces are, all the faces are nothing but each face. If I collect all the faces, then each face is nothing but a sample from a probability distribution of all the faces. Okay, so these are the samples that it is able to generate. And if you see in 2016, this is DC GAN paper, deep convolutional GAN paper. It is able to generate, these kind of faces. And today, in 2021, style GAN 3 paper is able to generate, these kind of faces, which is quite good actually. And here comes some kind of, sources. Now, flow of the slides. I will talk about concept of generative models, mathematical formalization, and then about distribution functions, probability distributions using neural networks, generative adversarial network, autoencoder, normalizing flows, and some messages, and also some homeworks. So first, the concept of generative models. For this topic is a discussion. What are the typical inference tasks in machine learning? Can we think application scenarios for this task? So I'm just giving you some tasks, examples of inference tasks. For example, prediction, seeing data X, predict T. T is the target in our terminology in machine learning. That is typically in future. For example, seeing channel measurements today, predict channel conditions later. Estimation, seeing data X, estimate T. Example, let's say seeing the symptoms, estimate infection status of a person, say whether the person is, let's say, got COVID. Okay, so that is an estimation. Classification, seeing data X, find this parameter or class for the target T. So typically this is supervised. For example, seeing channel X classifies condition, for example, so let's say this is a cat, this is a dog, or this is an apple, and this is an orange. So figure it out. Clustering, seeing data X attached to a class T. So this is typically unsupervised. And the example is some samples are bad, others are good. So inference tasks are prediction, estimation, classification, clustering. So I start with an example of wireless communication because, I talked I gave this tutorial for signal processing and communication, SPCOM. So that's why that I'm giving a simple communication example in this case. So this is a transmitter and this is a receiver. Let's say these are two antennas and some information is going through the channel. And a time-tested approach was use of linear channel. So you basically receive the signal X. Please note that here the target signal T, that which is going through the channel, and receiving signal I'm denoting as an X. So X is the signal that the receiver has observed. And then if the channel is H, this is the linear channel. So that's why it in H into T. And here, H, and this is the extra noise down. So we have to estimate the transmitted signal T, and we estimate the transmitted signal as T hat. A standard approach is a least square, X minus HT, norm square, that you minimize L to norm square, and everybody knows that the answer is the pseudo inverse. Okay. Now, the above is an example of a generative model. What does it mean? That means this signal X, which we observed, got generated by a linear transformations of the transmitted signal T through this linear matrix H. Okay, so the linear matrix is the channel information, and then the extra portion which you could not model, that may be observed in the noise, or this may be an environmental noise, okay, measurement noise, etc. So here the generative model is linear, and we have this time-tested approach of least squares. Suppose we do not know the channel, then how do we estimate the transmitted signal from the received signal using this above information? In that case, a standard procedure is to use the pilot signals, okay, and then estimate the channel. So that means that you basically send the known signal T, you known signal you transmit, receiver knows which known signal is coming. So that means T is known, X is received. It basically try to estimate H. Given after that, once the H is known, then a new T, unknown T is transmitted. X is observed, then because it knows H, now it can find out T hat using this equation. Okay. Now for nonlinear transformation, suppose the received signal X equal to some nonlinear function of the target signal T, and then channel and noise. So how do I write it? For example, any T hat, when we write it, this is some kind of, because X we observed, so it has to be some function of the X, right? So it is f theta X. So theta is the parameter in this case. So I can write a general transformation f theta X. In this case, it's a linear transformation. In some other cases, it may be a nonlinear transformation. Message. If we know the generative model, then that means if we know how data got generated, then inference is easier and interpretable. So this leads to trust. Now, mathematical formalization for machine learning. So it is a probabilistic formalization. You have the joint probability distributions. I'm just doing it, because I cannot show you complicated multidimensional spaces. So everything is drawn in 2 dimensions. So let's say this x1 and x2 are 2 variables. x1 is the x1 equal to x is a scalar observation, and x2 equal to t is the target. Okay, which let's say we want to predict. Now we can have a distribution like this. We can have a distribution like this. In this case, this is correlated, and here this is more uncorrelated or independent. So it is natural that if for the prediction or estimation problem, if I want to know what is the probability distributions of x2 given x1, in this case, it's very clear that the prediction problem will be easier for this kind of distribution if x1 and x2 are correlated, right, or not independent. Now, let us concentrate first on Gaussian distribution, because Gaussian distributions is our bread and butter in signals and systems. It is highly used across many fields. So Gaussian distribution has this particular form. Okay, somebody in statistics that found this particular form, meaning it's Gauss. So in this case, that for the Gaussian distribution, X is the vector, M its mean, and covariance. So it's only basically Gaussian distribution is only parameterized by second order statistics. So first order statistics M and second order statistics covariance matrix. It basically defines the Gaussian distribution, and that's it, right? And what is the rule? The rule is very simple, that this has to be non-negative. So this is the function. This is the function of the X, and given mean and covariance. So this is non-negative, and integration over this one has to be equal to 1. Fine. So just I'm showing you some examples of the Gaussian distribution. These are the real data points, and the Gaussian likelihood has to be like this, and the marginal distributions P of x1 and Px2 can look like this, right? So there are some properties. If jointly Gaussian, then marginals and conditionals are Gaussian. If the linear transformation of Gaussian is a Gaussian, if mean square error cost optimal estimation is even known, that is expected value of x given y. So that's called minimum mean square error estimator. Okay, and for case of a Gaussian distribution, minimum mean square error estimation for a linear model, it will turn out to be a linear estimator, that is called LMMSE, linear minimum mean square error estimator. Now Gaussian distribution is an example of a generative model, because once I know the Gaussian distributions, I can basically sample it, and I also can find out. I know that how the data got generated, so I can sample it, and I also know what is the value of the likelihood of a given source. Now comes a binary classification problem. Just to give you an example, that these are my blue points. So, and these are my red points. What are these points are? This is height and weight. So it is, there is a, let's say there is a practical scenario where we go to a random person and ask the person's height and weight, and also the gender. So if this is, women, then these are height and weight of that particular point. So this is the two-dimensional vector, and red points are for the women and blue points are for the male. Okay. So now if a new point comes in, new point means a new person comes in, it may be a task that what is the person's gender. Okay, so that can be a prediction task or a classification task. So how do we do that? So maybe that we will have a, we will try to model these points as a Gaussian distribution and the other points as another Gaussian distribution like this. So the red points for the, female, and blue points Gaussian distribution is for the male. That we figure it out. And then once we figure it out, it's very simple, because after that, the Gaussian distribution has this kind of a function. So then I equal to 1 and I equal to 2. I equal to 1 is the man, I equal to 2 is the woman. So these two distributions I know. So this is conditions on the gender. Then any new data points comes in, you basically, this is my function. This is my functional representation. So you basically get we basically get this x, put into this function, calculate which likelihood is the better, the red ones or the I equal to 1 or I equal to 2, or the red ones or the blue one, and then whichever is the maximum one, we figure it out. This is called maximum likelihood classification. And please note that this is an optimal classifier in Bayes minimum risk criterion sense. Okay. So steps up maximum likelihood classification is that we get data for each class. For each class, we model a distribution. Of course, we have to learn the parameters of the model distributions using machine learning, some framework. It can happen one class is Gaussian, another is non-Gaussian. When a new test input arrives, the test input class equal to the class for which likelihood is maximum among all classes in our experiment. We continue one by one for all test inputs, check the goodness of classification by a measure. So for example, accuracy. Okay. Fine. Now, this is the maximum likelihood classification. It has a little bit better brother. It's called maximum a posteriori classification. It also comes from the Bayes minimum risk criterion rule. So in that case, this argmax over the likelihood value is weighted by the prior probability of the class P of I. For example, let's say that, generally in our signals and systems area or computer science area, typically wherever I go in the world, in the audience, the number of women is typically much less. So if I knew this one compared to the men, so if I know this one, so according to that, I will basically, weight this evaluation criteria for my inference task of classification. Okay, so that's why this pre-I is the probability of the ith class that comes as a multiplicative factor with the likelihood value. Okay, so now comes Gaussian mixture model. I have told you about Gaussian. Gaussian is nothing but a multimodal, Gaussian is nothing but a unimodal distribution, one single mode. But if I have data, lying like this in the two-dimensional space, or like this, that means that we can fit for every mode one Gaussian, and that's called Gaussian mixture model. It is also well known, and this is also a generative model. The equation is like this. Here pi k is the probability of each kth Gaussian, and for kth Gaussian, it has its own mean and own covariance. And how do I generate this guy? Basically, let's say there is a switch, and the switch with the probability pi k is connected with one Gaussian, so for the kth, let's say for the kth Gaussian, and then from the kth Gaussian, we generate a sample. Okay, so if this is required. Message: if you know the statistical generative models and can compute likelihood, then inference is possible. Okay, so if I know the generative models and also can compute the likelihood, then inference is easier. For example, in this case, I have shown you the examples for classification. Now about distribution functions. Reasons for learning distributions, and these questions I asked to the audience. What do you think? What are the main reasons? Well, there is no black and white answer, but with my experience, reasons for learning distributions, two important aspects are generation of samples. We can draw new and new samples, and computation of likelihood. We know quality of a sample. Okay. Now, another important issue that once we learn the distribution, we can forget about the data, perhaps helps for security and privacy. Okay. Now, a distribution function is non-linear. Recall that the definition of a distribution function, P of x, has to be that P of x greater than or equal to 0 and integral of P of x equal to 1. Because of these two constraints, it can be easily show that, it does not hold, the Px function will not hold with respect to x, superposition principle. So this is not linear. Okay, it's a non-linear function. Any distribution function has to be a non-linear function. So, and there can be many types of distributions. I'm here giving a Gaussian as a multivariate example like this, and note that this is f theta x. So x goes through, and if f is the likelihood value, and this is the gamma distribution. Here tau is a single scalar variable, it's a non-negative scalar, and the equations looks like this. So this is the parameter, theta is the A and B of the gamma parameter. Here the theta is the parameter mean and covariance. Okay. So, and there are a bunch of exponential and other distributions, but we refrain to talk about them right now. And here comes some just for the Gaussian distribution, how it looks like, and for gamma distributions, according to the parameters A, B, how would that that look like? Okay. So how do I find out the Gaussian distribution parameters? Let's say I was only given the data points D, and a Gaussian distribution looks like this. This is my f theta x. F theta x is nothing but the likelihood value. This is that function. This function I'm writing as an f theta x with the parameter theta, and I would have to know from the data what is the parameters of this theta. Theta is the mean and covariance, so this I have to estimate. How do I estimate? So given a data set D, let's say there are n numbers of samples, xi, I equal to 1 to n. What is the estimate of the parameters? This is the mean, 1 by n, I equal to 1 to n xi, and the covariance 1 by n, xi minus m, and xi minus m transpose. This is well known. And how to estimate this parameter? There is a standard approach that this is called maximum likelihood approach. It's a basic approach in, if you go through any standard book like Christopher Bishop's book on pattern recognition and machine learning, that given this data D, these xi points, that what you do is that you put into this likelihood function value all these xi values, and then you assume that all these are independent and identically distributed. So you multiply all of them, I equal to 1 to n. You optimize this function, this whole thing with respect to this theta. So argmax over this whole thing. And if I do that, if I write all the lines, it is basically exactly analytically tractable. And if we do this one, then if we optimize this one, then we'll get this mean and covariance. Okay, so it is directly doable. Now, may suggest a distribution function is nonlinear with respect to input signal x, and we may be able to compute parameters of the distribution function using maximum likelihood principles. Okay, so these are some strong principles that which is basically age old. Now, probability distributions using neural networks. Here I'm showing a basic diagram of feed-forward neural network and structure, and in generally a fundamental block diagram that remained almost same for last 60 years. So what happens that if we check in the internet, this kind of, if we write feed-forward neural network or neural network, artificial neural network, this kind of such words, we'll get this kind of images. What is this image is telling you? X1, X2, X3. This is a three-dimensional input, X. And I'm getting, this is a single layer neural network. There is one hidden layer here. And then the output is T1. It's a two-dimensional output, that is T1 tilde and T2 tilde. Okay. And here, these A11, A12 are the weight values, and Z1 is nothing but the combinations of all of them, X1, X2, X3, weighted by these A11, A12, and A13, like this. So you can easily see that the Z has, let's say 4 Z1, Z2, Z3 equal to Z4 equal to nothing but this equal to AX, and AX has these weight values A11, A12, A13, X1, X2, X3 are there. So these are sitting in, and if we construct this one, it will be T tilde will be, like this function. So O is the output weight matrix. So I can think it like this, nothing but linear transform, nonlinear transform, linear transform, like this. So in practice, if I have a neural network, typically, let's say just a feed-forward neural network, it looks like X is going through, and some output will come out, It's a linear transform, nonlinear transform. That is the one layer, first layer, linear transform, nonlinear transform. There's a second layer like that, linear transform, nonlinear transform. Typically, the nonlinear transforms are the activation functions. Okay? And then finally, the target as a output. Okay. Now, so you can easily see that the neural network, because of the nonlinear transform sitting here, basically they take this X going through this one, and it produces an output, which is the nonlinear functions of the input. So if this is true, so can you use a neural network as a distribution function? Because distribution function such that we can draw samples and compute likelihood. I mean, can we do that? Note that the neural network can have arbitrary nonlinearity. So distribution function is the neural network. If I do, then the target T is nothing but a likelihood value T, and that may be, let's say, f theta x. Okay. So if this is the likelihood value, so we can compute an optimization problem like this. And this target output, if this is the likelihood value, this is parameterized by the parameters of the neural network, and that is theta here. So maximum likelihood approach will be, I take this several data points xi and optimize in the maximum likelihood sense, this likelihood function. So given we learn a neural network based distribution function with maximum likelihood optimization principle, is the learned function useful? Please recall that aspects that I generally for a distribution, we generally want a data sampling and likelihood computation. Okay, these two things we typically wish. Now, a problem will be to generate a sample if I construct just now that what we talked about here. Okay, in this way, if we can construct, because given f theta x is a likelihood function that is coming from a neural network that which I've shown you, that note that we may compute the likelihood, but it may not be easy to generate a sample. Okay, why? Because I don't know how to generate a new sample x. For example, now the question is that how to generate a sample from a Gaussian distribution with given mean and covariance. Understanding that requires understanding of generation of samples. How to generate a sample from a Gaussian distribution with given mean and covariance is like this. Let's say Gaussian distribution has this standard, functional representation. It has distribution parameters theta equal to mean and covariance. Now the fact is the linear transform per Gaussian source is Gaussian. So what we can do is that, let's say that I have to generate a Gaussian distributions like this with certain mean and certain covariance. This mean and covariance is given to me, and I have to draw samples from that mean and covariance. So what I do is that I use a random number generator, which is well known, let's say, or very standard in programming. So, so I take a Gaussian random number generator, Z. Z has two, it's a two-dimensional Z, Z1, Z2, which is coming from N0I. So it's an isotropic Gaussian. Then for this covariance matrix, I calculate the singular value decomposition. I calculate U sigma U transpose, then write U sigma half, U sigma half transpose. So U sigma half, U is nothing but the same dominant singular values, and sigma half are nothing but the singular values in a shorted out, let's say in an ordered sense. So the algorithm steps to generate data from the certain mean and certain covariance for a Gaussian distribution is that draw an IID Gaussian sample Z N0I and generate an intermediate Gaussian variable Y as U sigma to the power half into Z, because U sigma to the power half is computable from the covariance matrix that which is specified to me, and then take this Y and then shift it into this Y still have the zero mean, shift it through the mean vector M. So you basically take Y plus M. We are done. Translate to so this is nothing but a translation in the algebraic space. Okay, so how it looks like? It looks like that I have a Z here sitting here. I have a matrix multiplication, linear transform. I add a bias term, that is the mean value. I get an X output. That means this X is coming from this Gaussian distribution mean and covariance. Okay, done. So sample generation is in a neural network is that if I can think it like this, then can I extend it? Can I, can I generalize it? That okay, this matrix multiplication is nothing but a linear transform. So now can I do like this? Z is getting into, and now I have a matrix multiplication, linear transform, then a nonlinear transform, linear transform, and nonlinear transform like this. There are several layers, and then X is coming out. So X is coming from this functional representation, let's say f theta X. But, and no, sorry, X is coming through a transformations of this Z. The transformations I did not write, but I'm assuming that this X is coming from this functional, this distribution f theta X. So the idea is that excited DNN with IID Gaussian sample to generate a sample. So a neural network now can be a generative model. That means I basically excite the neural network with a random, isotropic Gaussian, or it's basically nothing but a Gaussian noise, okay, of Z, that which is sampled from this N0I. I excite the system and generate an intended, data representation that is X, and X is coming from my intended distributions f theta X. So excited DNN with IID Gaussian sample to generate a realistic sample. Not all neural networks are not generative models, but some can be. The message is that generally our understanding is that noise is bad in a sense, but now we see that noise is helpful, because noise is basically the driving noise to excite the system to generate realistic samples. So this is nothing but a clever engineering. Now, generalistic real samples. The problem is that we talked about when we talked about the Gaussian source, there the function was f theta X. F theta was the Gaussian likelihood function. But here I can conceptually think, though I will be able to generate X through this nonlinear function, but what is the likelihood function f theta X? That I do not have in my hand. So it is difficult to, or non-trivial to use this maximum likelihood optimization approach like this, okay, to learn the parameters of this neural network. So message, generating realistic sample is not trivial, okay. Now comes generative adversarial network, GAN. So the GAN principle is a wonderful idea. We can generate samples, but we may not need, the explicit form of this likelihood function f theta X. What is the idea? So this is the architecture. The idea is that these are the real samples in my hand in a data set. And this is a generator. Generator is nothing but a deep neural network. And by the time that when this GAN came, by that time, the deep neural network-based classification was pretty strong. So here I have the discriminator. This is the deep neural network-based classifier. So the idea is that this generator is excited by a noise input. Let's say Gaussian noise input. So it is like this. It is generating and creating an X. So this X is here. So this is a generated sample or a fake sample or an artificial sample. On the other hand, these are the real samples. Now there is a discriminator here. So the discriminator is a classifier. It basically does a simple binary hypothesis testing problem. It's a two-class classification problem. That is this a real sample or is this a generated sample, okay, or fake sample? Now, what happens that the generator tries to generate samples. So they play a game between each other. And the game is that generator tries to generate a sample such that this sample is so good that the discriminator cannot figure it out that whether this is a real one or a fake one. On the other hand, the discriminator also wants to be strong by itself such that it does not want to be get confused that this is a real sample or a fake sample. So they play between each other, and some point of time they stabilize and nobody improves in the standard game theoretic notion. And that at that point of time, we can think that, okay, these samples are so good that the discriminator cannot figure it out that whether this is a real sample or a fake sample. That means this guy is good enough, okay? And here I show you some style GAN images generated by NVIDIA, image created by NVIDIA, and generated some generated samples that which looks pretty impressive. So GAN is an implicit distribution. It can generate samples, but it cannot compute likelihood so easily. And GAN has many applications today, like high dimensional probability distributions, use of GAN in data limited learning. GAN is in model-based reinforcement learning, denoising, etc. I'm skipping this portion. Now, training process for the vanilla GAN basic GAN This is an iterative algorithm using stochastic gradient descent and mini batches. In each state out of the iteration, 2 mini batch samples, one from the true data set and another from the latent. Latent means this is Z. Okay. And 2 gradient steps in alternating fashion. One is to optimize the parameters of the discriminator for minimizing the discriminator cost. Another is to optimize the generator parameters for minimizing the generator cost. Okay, so this is the way it works. Hopes is that with the hope that the optimization procedure converges to a stable point. Finally, we get realistic samples. And how to define this classification cost, JD theta D and theta G for the discriminator D theta dx. And what kind of loss functions are useful? Actually, these are some kind of cross entropy based loss function. And here comes one example. Okay. And this is basically collected from Ian Goodfellow's NIPS tutorial. So I will further suggest the audience to go through the NIPS tutorial. Here I have the basic points. Okay. Ultimately, it can be shown that this is nothing but a min-max problem of a value function. And there are many other types of defining cost functions. One famous cost is optimal transport cost, and for Wasserstein distance measure based GAN. And here is the paper. We also have worked here with Wasserstein distance. And we can see that how the GAN improved over time. That is the original GAN paper generated samples, 2016, 2014, 2016, and 2021. You can easily note that, this is the example that I gave you in the very beginning. So we can easily see that, how the sample generation process improved over the time. Now, the message is that GAN is powerful. Now comes autoencoder. What is an autoencoder? The concept of the encoder and decoder for in standard source coding methodology like video audio codecs such as MP3 and MPEG. Okay, and here comes some source. Let's say, what is the system transformation that, let's say this is the system, X goes into and Y comes out. And what I want Y as a solution. Let's say arg mean over B, X minus B square. B is there something that which I'm trying to optimize. In that case, B is nothing but equal to X, right? If the B has the same dimension of the X, otherwise this, this norm is even not valid. So the system is an identity matrix. So this is the identity matrix. That means this has to be an identity matrix. So if I write X is an identity matrix, X comes out. So can I generalize this one? X basically here the matrix A. So Z is nothing but AX. And then A is invertible. That means Z goes through A inverse, then X comes out, right? So in this case, it's a perfect reconstruction. There is no loss of the X. And I have the dimension of X, dimension of Z has to be dimension equal to dimension of X. Otherwise, A inverse does not exist. Now, further extension is that, can I assume that the dimension of Z is less than dimension of X? And I have a linear transformation A, that's a fat matrix, and B is a tall matrix. So arg mean over X minus Y L2 norm over A and B, which A and B will have that. That is basically, you can think of it as a principal component analysis. If X is Gaussian distribution, we can compute its covariance and then find out the singular vectors, and the singular vector transpositions is basically the dominant singular vector transposition construct this matrix A. Now, further extension is this: if I have this one, then can I think that instead of linear functions, I will use some functions, arbitrary functions, f theta and g phi, okay, which comes out of so X goes through the function f theta, it goes as Z, Z goes to g phi, it comes out as an Y. So in that case, the optimization cost functions will be X minus Y L2 norm, argument over theta and phi, where Y is nothing but g phi in argument Z, and Z is nothing but f theta X. So can I write it this? And this is my constraint, and this is my optimization. So can I find out what theta and phi this is going to happen? And typically dimension of J is less than dimension of X. And dimension of X minus dimension of Z is some kind of compression, saving of dimension is the compression. So this is the general compression architecture. Now, if F and G can be DNN, then it is called deep autoencoder. Okay. So given data points X, this is nothing but, xi minus yi. It's an unsupervised method, xi minus y square. This I minimize such that yi equal to g phi f theta xi. This is the case. So what we can see, the architecture is looking like this. X basically, this f theta is the function or the transfer function by which it compressed to z, and from z it again extended to y. So this is called encoding function. This is called decoding function. So encoder and decoder, and this is the latent variable. How to use the autoencoder to generate a sample? Because once this training process is done, we can forget about that. We do not need this portion. Only the G is a latent that is basically coming from one distribution. We pick, we randomly generate a Z, pass it through that decoder and generate a signal Y. And that Y, because of the optimization, we believe that that's a realistic sample. And how to use this for denoiser? It is the same similar concept, because I have this X, which is, let's say, the noisy sample of the true X. Then I know that, for example, for principal component analysis, this is there is a signal portion and there is a noise subspace. There is a signal subspace and there is a noise subspace. It's nothing but signal subspace are toward this dominant eigenvectors or singular vectors, and the other portions is the noise subspace. That means those dimensions we need to cut out. So here, by doing this process in the timeline at the time of learning autoencoder, and we cut it down to the Z, which is a much smaller dimension, there the informations all exist. Other portion, there is no other dimension, there is no signal. Actually, there is no information for signal generation. So the noise will sit there mostly, and we can denoise it. So if this is a noisy signal here, and then we pass through this one, noise basically gets filtered out, and then here the denoise signal comes out. Now comes variational autoencoder. In this case, the Z, because for the Z to take a prior distribution, we want Z to have a Gaussian distribution like this. So at the time of learning, we have a penalty like, a KL penalty like this distributions of the PZ has to be closer to a Gaussian distribution. This we add in the optimization procedure and learn. Then come normalizing flows. Normalizing flows, this is using a change of variable rule in probability theory. There exists an invertible differentiable function. So now assume that the F, this can be a deep neural network, but this is the invertible function. Okay, so that it's a bijective function. That means if I excite this G to create my X, then from the X I can go back to the Z. That means for Z space and X space, it's a bijectivity holds. Okay, so for each G there exists one unique X. If this holds, that means the functions, these transfer functions have an inverse, F inverse, that means I can use the change of variable rule in probability theory and calculate the likelihood of the X, Pxx, as using this formula. Okay, so Pz is, let's say, Gaussian distribution. So in the Pz, F inverse X is nothing but it's a representation of Z. That which is basically inverse map or image of the X in the Z domain. So I know PZZ, and that PZZ has to be multiplied by determinant of the Jacobian of this function, inverse function del F inverse X, del X. And this we can calculate and then multiply it with that one, and I can calculate the likelihood of a PX. So the algorithmic procedure to compute likelihood is that given an X, let's say the system is known. So given an X, go from X to Z. So this is a reverse transformation. Compute likelihood in Z domain, that is this part, and then compute likelihood of X using change of variable rule. So that means this Jacobian has to be multiplied. Okay, determinant of the Jacobian and amplitude of that has to be multiplied. Now, algorithmic procedure to generate samples. Once we learn the system, I don't need this guy at all. I don't need this part at all, but I only need this this transfer function. So because I know the F, so I basically pick up a Z, a sample Z from the isotropic Gaussian, generate Z X using this forward transformation. That's it. So normalizing flow is an explicit distribution. It can generate samples and it can compute likelihood. Normalizing flows are several types, like real NVP model, glow model, autoregressive flows, residual flows, etc. And we also have mixture of normalizing flows because, you know, normalizing flow is one distribution. So I can have multiple distributions, and that summed up as a linear combinations of several distributions like this way. And we have this, so this is the, you know, sum of several distributions, and pi k is the prior probability of each distribution. So Z is exciting each normalizing flow and generating X, and X is coming from such a, you know, such a mixture distribution. So these also we have, and this is our paper in IJCNN. Okay. Now, what are the technical challenges? Mainly learning parameters from a sample data set, how to write expectation maximization or variation berries, and how to combine back propagation and expectation maximization. We are able to do that, okay? That it is possible. Now, interpolations in latent domain. So here I show you some examples of the interpolations in latent domain. Here, you know, these are handwritten digits. These are the real digits from the MNIST data set. And this is also another set of handwritten digits. And this zero is slowly, this zero and this zero is interpolated and created, you know, different kinds of, and we create, you know, samples according to the factor of this interpolation. So in this case, what you do, let's say that this is my X1 and this is my X2. So these are two samples in the space, in the X space, that is X1 and X2. So for X1 and X2, what you do is that, let's say there is a normalizing flow sitting here. That's a neural net, which is basically, you know, invertible neural net. So from the X, let's say this is, I can go to Z, from Z I can go to X. So let's say this is my X1, I now go to Z, that is Z1, and there is an X2, I go to Z2. Now for X1, I go to Z1, X2, and I go to Z2. These are unique relationship. And then in the Z domain, Z3 equal to alpha 0, 1 plus 1 minus alpha. Z2 alpha is between 0 to 1. I can vary these alpha in different steps to create in a Z3. And then using Z3, I excite the neural network and create X3. So from X1 to Z1, X2 to Z2, Z3 equal to this, and then Z3 passes through this neural network again to create X3. And alpha is a user choice. So you vary the alpha and create different X3, and this is our you know, creation. And you can see here, this is a shoe and this is the shard. So shoe and shard are interpolated between each other in the latent domain, and then these are the images are created passing through the neural network. So these are all fake images, so, or artificial images, and it can be easily seen that the power of the interpolation in the Z domain is very, very powerful. So a normalizing flow is a powerfully explicit distribution. So we can use normalizing flow for maximum likelihood-based machine learning principles, training, and classification. So there are some messages. This is the tree view of the deep generative models. Note that it's not a comprehensive view. Generative models, here I'm basically mainly consider probability distributions. There's explicit distributions and implicit distribution. Explicit distribution means sample generation and likelihood. Both it can do. Implicit distributions means sample generation, but not likelihood. It cannot compute the likelihood. GAN is one prominent example of that. Now, of course, of explicit distribution, tractable distributions, and approximate distributions. Tractable distributions are fully visible belief nets, example like web nets, nonlinear PCA, normalizing floats, etc. And approximate distributions are variational autoencoder, markup chain like Boltzmann machine, etc. Okay, and these I have collected from NIP 2016, but this can be further improved today. Take home. Neural network-based generative models are powerful. Two main types, implicit and explicit distributions. GAN, autoencoder, normalizing flows are useful. Normalizing flows can be used for statistical machine learning. Now there are some homeworks, so please go through, these websites or some of the papers. I will now quickly go to generative dynamical systems. Specific case is hidden Markov models. So in case of hidden Markov model, we have let's say this is a speech signal. Speech signal looks like this, and this is its spectrum representation. In the this is called spectrogram. So here is the time, and here the frequency component window wise is called short time Fourier transform, and its amplitude is taken here and plotted. So you can easily see that short time Fourier transform is nothing but it's a periodogram. This is nothing but a power spectrum representations over time, and power spectrum is nothing but the Fourier transform of autocorrelation function. Autocorrelation function is the second order statistics. So from there we can see that how the statistics of the source slowly changing over time. Okay, we can easily see that. Okay, this is the representation, and this is nothing but a dynamical signal. So I'm straight away going to the dynamical signal. So a data sequence is an X bar. So it's a sequence with respect to time. So xt is the time at the tth time point, the vector, data vector, what we are seeing. So x1, x2, x3 like this, the data time points are indexed up to capital T xt. And there is in this modeling of the hidden Markov modeling, I'm talking about the hidden Markov modeling because this is conceptually simpler, because this is a discrete time based modeling sequence and the states are finite, but we can also try to extend this one for continuous state systems. So the corresponding state sequence is bar equal to S1, S2, ST. What is this state sequence? State sequence is the hidden state sequence. The idea is like this, that this is the generative model. In this generative model, there are several sources. So if there are n numbers of subsources, which are always active, these n subsources are typically independent between each other. And when they're independent, that means that all these subsources, let's say they are Gaussian distributions. So for every Gaussian distribution, generating Gaussian sources, and any time point t, xt, it is connected with one such distribution. So if the time point t, if this switch is connected with one such distribution, this xt is coming from that distribution. Okay. So conceptually, it means in the algebraic space, I have several distributions are several distributions with different means and covariance. Let's say for Gaussian distribution exists in the algebraic space, and then at any time point xt, the switch is connected with one of them, and then according to where it is connected, from there this one vector got generated and coming out as an observation. And how these switches the switch is behaving to have a temporal correlation or time-wise correlations over time, that st is a Markovian, so st depends upon st minus 1. So the state at time point t only depends upon the previous time point t minus 1. Okay, and for every state, that is p of x given x, the distribution, this is called state distribution, or this is called output probability distribution, that can be a mixture of several Gaussians or mixture distributions. It can happen. Okay, so and with respect to hidden state, HMM is parameter by three main parameters. One is called Q, that is the initial state probability distribution. Then there is a transition probability matrix, that is A, and there is an output probability distribution, that means those parameters of the every state distributions. Now here I show you a time state-wise graph. For example, let's say that the hidden Markov model as an underlying state, S1 starts from the state number 1, and then S2, it is state number 2, but at time point t equal to 3, it is still state number 2. At time point t equal to 4, it is still state is 2, and then from at time point 5, it jumped to state number 4 like this. So this is the true one. Okay, so this is the true state, underlying state inside. Now, if I know that this HMM is a generative model, and if I know the generative model, so lambda is the model that which I know, then for any sequence X bar, I can calculate P of X bar given lambda, any time length. Okay, capital T, it can be, capital T can be 10, capital T can be 100. Okay, for that, we can compute that Px given X bar given lambda using some standard algorithms called forward algorithm. Once I have that one, then I can use it for, let's say, for different classification purposes, like, you know, I have a sound A, I have a sound E, I have a sound A, I have sound E. So there can be different time lengths, but I can still, for every, you know, class, if I have a state, I can, sorry, for every class, I have a model, HMM model, then for any new sound comes in, and then that is this X bar, new, sequence, new sequence comes in, that is the X bar that I fit into the HMM model and can calculate the probability of X bar given lambda C. Lambda C is the model, HMM model for the Cth class. So for every class, you figure it out, this one, and then according to the maximum likelihood principle, do the maximum likelihood classification. And there is a way also that how to train this HMM model that also can be done by maximum likelihood HMM training. So for example, the HMM can be, you know, trained using expectation maximization. Okay. So overall representation is like this. Now every state, I can have a, you know, distributions where I need to compute the likelihood. Now typically the Gaussian mixture model is used. So, but here, as we have the formulation of the normalizing, normalizing mixture model, that means the mixtures of normalizing flows, I can bring in that one and put it there, because for that, for the NMM model, normalizing mixture model, that we can compute the likelihood. So it fits into the HMM framework and can model the dynamical sequence. Now, we do not need, in this case, any discriminative training. We can do everything according to the maximum likelihood classification principle. So I'm just giving you an example for phone recognition. So this is the performances by, in this paper, the PyTorch called the speech recognition toolkit for standard phone recognition for timid data set, 39 phones. This is the performance like 86.2%. This is the ICAS paper 2019. And then they had a paper 2018. This was 85.1%. The similar group that where they used light-gated recurrent units. That it's nothing but, you know, some kind of RNN to do this job, which is a discriminative training, I believe. So the ballpark number is around 85 to 86%. Note that all these results for clean training and clean testing. Now, for us, that what we can do is that we can use the HMM based maximum likelihood principle to classify. It's not a discriminative training. And here we got GMM HMM got 72%, NVP HMM, that where we use the NMM model, that where the normalizing flows are NVP model, that got 76.9%. And then for another one for the GLOW models, that we got 78.1%, which is still below than 86%, but all of them are nothing but none of them are discriminative. It's everything generative model based. So it's natural that I can simply bring all of them together as a committee machine approach, that, you know, we apply all these three models now, and then if the two is giving the same vote for which class, choose that one. Okay, that's what we do, and then suddenly the performance shoots up to 86.7%. So it is possible to use the generative model to get a similar performance like discriminative training based methods. Okay, and this is close to the state of the art without discriminative training. Okay, thank you for this tutorial. Please enjoy the tutorial. Thank you. Bye.